Next results, I will write them down, but I will not give proofs of those. First one is so-called Hilbert's lemma. Hilbert has a lot of work, of course, in mathematics, in algebra, in analysis, and this is something he has done in geometry. Let M be a point of M which is a surface in R3 such that A1 has local maximum at M, A2 has local minimum at M, and let's say this is strictly larger than this. So K1 is the larger eigenvalue, was the larger eigenvalue. Which one was larger? K2 was larger, right? K1 was larger.
K1 is maximum K2.
Okay. But anyway, the conclusion is this. Then Gaussian curvature at this point is non-positive. So this is a technical result. A technical result. And a consequence of this is the following theorem. This result is used in the following theorem. This is by Liebman. I'm not sure if I am pronouncing it correctly. If there is a compact surface in R3 with constant Gaussian curvature, if the Gaussian curvature is constant, then M is a part of a sphere. It is a part of a sphere of radius 1 over square root of 2. Well, you should, of course, object to this. Why K has to be, it has to be positive. Well, since it is compact by the previous theorem we just proved, you know that Gaussian curvature is positive at least at one point. But by assumption, we say that it is constant Gaussian curvature. Therefore, Gaussian curvature is positive at all points. And it's a constant number. And 1 over square root of K is the sphere which contains the surface. Okay, so this surface is contained in the sphere of radius 1 over square root of Gaussian curvature. So I will not prove this theorem either. Its proof relies on the Hilbert's lemma. Actually, my course I gave 2 years ago during the pandemic. I have lectures, video lectures, of these results. So you may look at those videos and see the proofs. Proofs are in the notes, but I have also video lectures. Okay. All right. So I will not go into the proofs of these. Oh, don't ask me that. I don't want to spend more time. In the remaining half an hour, I'll talk about so-called Gauss-Bonnet theorem. I will not prove this theorem either, but explain what it tells us. Okay. The statement is this: if sigma g, so this is my surface, is a compact genus G surface, in R3, then the integral of the Gaussian curvature over the surface. Okay, if I have this case in theta is 1, then this is the surface area. Okay, surface integral. So this is like weighted surface area. I compute the area of the surface, but at each point I plug here the curvature. If the curvature is big, then surface is kind of the area is enlarged. If the curvature is small, then it is kind of contracted. Of course, there are points where k is negative and so on. The thing is that this is just equal to 4 pi times 1 minus g. And what is the genus of the surface? Genus is the following. Any surface in R3 has the following type. It has forms like this, and it has usually G many holes. If G is equal to 0, G is surface, G is 0 surface, it means it has no holes. Then it's a sphere. Okay, it's just a sphere. So sigma 0 is the two sphere. Sigma 1 is split or donut. Okay, sigma 1 is this. Sigma 2 is the surface which has 2 holes, and so on. The nice thing about this theorem is the following. Here, Gaussian curvature is something very geometric. It tells us how the surface is bended, right? How the surface bends as you move on the surface. But this thing is not geometric at all. It's a topological invariant. 4 pi times 1 minus the number of holes. Okay? So the beauty and this strength of this theorem is that. I mean, here we have something geometric, but if you add up all this geometric information, what you end up is not geometric at all. Well, it is again, of course, geometric, but it is something more than geometry. It is something topological. Okay, it is deeper than the geometry. Even though the theorem is called Gauss-Bonnet, Gauss didn't write this theorem. He didn't prove this theorem. Bonnet didn't write and prove this theorem. But their work was used to prove this. Okay, so they were not aware of this theorem, but still we call it Gauss-Bonnet. Okay. Sketch of proof, idea of proof. For this theorem, you should just know the statement, okay? Nothing else. Nothing else. Idea is the following. I'll actually describe 2 different kinds of proof. The first one is the following. Suppose your surface locally is given by as the zero of a function. Okay. Suppose your surface is given like this. Now, every surface locally is given by the zero of a function, right? And what is the normal vector here? Normal vector u. So x uv, the parameterization is this uv f of uv. And it was your exam question. Normal vector was this. Minus f sub x minus f sub y, 1 divided by this, right? This is the normal vector. This is the unit vector. Therefore, this is the point on the actually sphere. So you have a map from your surface sigma g into the sphere, which takes any point to sigma p, which is just the normal vector at the point p, which is this gadget, okay, normal vector. A unit normal vector can be considered as a point on the sphere. So, and this map is called Gauss Map, okay? Gauss Map. And the nice thing about this map is the following. The miracle is this. There is this area form on this. You know from advanced calculus, how would you compute the area of this? The area form on S2, the area form W on S2 is what? On the sphere. It is this. X dy dz, y dz dx plus z dx dy. Okay, this is the area form on the sphere. And the miracle is this. If you pull back, so this form lives here. It measures the areas of, if you give me two tangent vectors on the sphere, it, so if you plug this point vectors into W, omega, you compute the area of this, piece of tangent plane, and the integral of this gives us the area of the sphere. So I have this. Its integral over this is the area of the sphere, which is 4 pi r squared, but r is 1 since it's the unit sphere. The fact is, the miracle is the following. If you pull back this form via this function, this is just pure computation, okay, pure computation. If you pull back that form over sigma g, you get the Gaussian curvature. You get this. Okay, so you get f sub. Okay, you get Gaussian curvature times ds, and that is more precisely the following: f sub xx, f sub yy minus f sub xy squared, 1 plus f sub x squared plus f sub y squared, 3/2 dx raised dy. Or, okay, if I am using u and v, actually, okay, yani bunlar aslında u, v demen lazım da, şöyle diyeyim, I'm sorry. u, v, u, and then u, v, u. Therefore, hence, we just need to compute this. We need to compute this gadget. So I would like to compute this, right? Yes, but this is just pullback of what? Pullback of omega. Okay, because this fact tells us that, you know, instead of computing this, I can compute this. And then what you do, you need some so-called you need some other topological tools to compute this gadget. We use so-called cohomology. Actually, the RAM cohomology. Of surfaces or manifolds. What is the RAM cohomology? The RAM cohomology is basically closed forms divided by, so it is something like this. Let's say, for example, the RAM cohomology of the surface is this. The set of all two forms, closed two forms, on sigma g divided by exact two forms. Exact two forms means d of something, okay? D of eta or nu, whatever. If it is differential of something, then it is called exact. And what about two forms? Actually, any two form is closed on surface because surface is two-dimensional. So this is an object. This is a vector space, and you have to make use of this. Okay. Using this, you can compute this, but along the proof, you need some other things. You also one also needs some analysis, like approximation theorems. Nedir? Continuous fonksiyonları mesela şeylerle, polinomlarla non-Weierstrass approximation. Approximation theorem. And some vector bounding theorem. So this, you know, even this kind of easy fact requires almost all kinds of mathematics. It requires geometry, topology, analysis, and actually vector bounding and so on. I will not talk about this proof. Other than this, you may look at my videos. You may check my math 505 videos. Okay, that I have more detail. But there is another proof, second proof. This is more what this is the one which uses Gauss's work. Gauss show the following. If you have a surface, let's say sphere or some other surface, let's say something like this, or just plane, okay, plane. And suppose you have a triangle or any other surface. It doesn't have to be one of these. It can be any surface. Suppose you take the triangle in the surface. On the sphere, the triangle is not really a triangle, right? What I mean by a triangle, actually I should say geodesic triangle, meaning that we have to pick curves joining these 2 points, which has shortest distance. On Earth, the shortest distance are the geodesics and they are great circles. So this is a part of a great circle like this, and then another great circle, and then another great circle. And if you compute these angles, let's say theta 1, theta 2, theta 3, okay? If you sum these angles up and subtract pi from this, what you get is the following. Integral of the Gaussian curvature on this triangle T. Okay. Here, yes, yeah, you're right. That's true. So this means for a sphere, of course, this is always positive Gaussian curvature, so it's the positive number, meaning that the sum of the interior angles of a triangle is always larger than pi. So the sphere, sum of the interior angles of a triangle is larger than pi. If you choose a surface like this here, Gaussian curvature is positive. Here, Gaussian curvature is negative. So in this case, the sum of the interior angles will be less than pi. Okay, so something like this. Suppose we have a triangle. Okay, geodesics will be like this, and let's say theta 1, theta 2, theta 3. This time, some of these angles will be negative. Okay. But this is, Gauss's formula for a geodesic triangle. Or, of course, a Euclidean plane, right? From elementary school that if you sum the angles, it is always pi, right? Theta 1, theta 2, theta 3. So theta 1 plus theta 2 plus theta 3 minus pi is the Gaussian curvature times ds over this triangle. But on the plane, Gaussian curvature is always 0. Therefore, this is 0. Therefore, the sum of the angles is pi. So that's another proof why the sum of the angles on a plane is always pi. Okay. And how can we use this to prove this theorem? Let me talk about that in the last 10 minutes. Okay. Now, proof of Gauss-Bonnet. Okay. All right. Comes better. You take the geodesic triangulation of the surface. Here I say something as if it is easy, but that's not easy either. So what I mean a geodesic triangulation is this. You take points on the surface and you divide your surface into triangles. But all these triangles are geodesic triangles, okay? So the edges are always shortest paths among points. This is what we call a geodesic triangle. Okay, say T1, T2, Tf are is the list of all triangles. Of the triangulation. In the books, they refer to a paper, a research paper, written like more than 100 years ago. I guess it is 1920s. I forgot the name of the guy. I checked the paper, but I actually didn't see the proof. I mean, I didn't understand, how. But it's probably my mistake. But what I'm trying to say is that it's not something easy. Okay. However, if you assume this, that such a triangulation exists, of course, if you are given a surface, you can do this. We can do this, but whether it is possible for any surface is something else. You have to prove it. And that is not easy. Now, so my surface now is the union of these triangles. First triangle, and then the second triangle, and then the last triangle. PL. F here stands number of faces. Okay, how many triangles we have? Each triangle is called a face. Okay, now let's take the one. Okay. I, take the 2I, take the 3I, be the interior angles of TI, the I triangle. Okay, I triangle. İlk ispat, tarif ettiğim ispat daha o yüzden bence complete. Hani buna göre. Ama bu da çok daha anlaşılır bir ispat. Böyle dediğim gibi matematik çoğunluk sürümden bir ispat. Peki. Okay, now I would like to compute this. But this surface is just union of I from 1 to F, right? So this means these are these triangles. Okay, I write these triangles. T1, T2, T3, T4, and so on. But we have finitely many triangles. I can write this as sum over I of the integral of the Gaussian curvature L over the triangle TI. But Gauss showed that this thing is just what? This is just sum of the interior angles minus pi, right? So this is just theta I1 plus theta I2 plus theta I3 minus pi, right? Here, the I triangle is this, let's say. The I. So this is theta I1, theta I2, and theta I3. Sum of the angles minus pi. What is this? Well, you sum over all the triangles, right? All these angles. So what is that? This is the sum of all the angles of all triangles minus from each term I get a minus pi, so f times pi. Okay. Now, what is this sum of all the angles of the triangles? Well, take any vertex, okay? Take any vertex like this. And then at this vertex, there are triangles, several triangles. One of them is like this, the other one is like this, and so on. This is the first triangle, let's say, and it has angle, some angle. So this is I. This is the I triangle, this is the J triangle, and it has some angle here. Say this is the first angle, this is the second angle of that triangle. This is the first angle of the K triangle, and so on. What is the sum of all these angles? Well, this sum is just 2 pi, right? These are because, the angles are here just the angles between the tangent vectors, and tangent vectors just divide the plane into some pieces, but the sum of the angles again 2 pi. So this thing is just that 2 pi times what? Times the number of vertices, right? For each vertex, the sum of all these is 2 pi. So this is 2 pi v minus f times pi, where so I have this integral is just 2 pi v minus this, where v is the number of vertices of the triangulation. Yani kaç tane vertex var? En sonunda da şunu yapacağız. Finally observe that each triangle has three edges, and each edge is shared by two triangles. Değil mi? Her bir kenar iki tane üçgenin kenarıdır. Ve her üçgenin de üç tane köşesi var. So if you use this information, you get this. This means, so number of all the vertices is 3f because each triangle has 3 vertices and I have f many triangles. So before I glue them, I have 3 times f times vertices or edges. 3 times, okay, each triangle has 3 edges. I'm counting the edges. The number of edges before I glue those triangles is 3f. But when I glue them, each edge is counted twice, right? So they come together and become one edge. Therefore, this is just 2 times 2. Okay? And if you take this over here, you get this. This gadget is 2 pi e minus f. This, okay, let me write it this way. F over 2, and that is just 2 pi b minus e plus e f over 2. I plug and subtract e here. B minus f over 2. I plug plus e and minus e. And then write it this way, 2 pi times b minus e plus 3f over 2 minus f of 2. Bunu nasıl yaptım? Okay, yeah, here e is just 3f over 2. So instead of this, I write 3f over 2. So what you get 2 pi times b minus e plus f. So number of vertices minus number of edges, not plus number of faces. This is something you are familiar with from elementary high school. Right? This is just for a sphere. This is 2. Right? Euler's formula. If the genus is larger than 1, it is not 2 anymore, but it is 2 minus 2g. And this is called Euler characteristic. Euler characteristic of the surface. Of course, this passage, that this number is 2 minus 2g. No matter how you take your triangulation, this is always 2 minus 2g, is another topological fact, and it is not easy either. We need homology. It's another graduate course, okay? But this is how it is proved. So this integral is just, if you take 2 outside, you get 4 pi times 1 minus g. Okay? And this has many generalizations. Generalizations include many theorems in all kinds of branches of mathematics and physics. Okay, if you write Gauss-Bonnet theorem in physics, you will get hundreds of articles about it. Okay. Umarım sizin için de bu ders benim olduğu kadar zevkli geçmiştir. Yani burada dediğim gibi işte her şeyi aklınızda tutmanız gerekmiyor ama neler var? Hani işte Gauss'un yaptığı işler nelerdir? İşte curvature nedir? Connection nedir? o tip geodezik nedir? Bunları aklınızda tutsanız yeterli. Yeri geldiğinde de açıp okuyup tabii ki hani tekrar reproduce edebilmeniz iyi olur. Aradan zaman geçerse onu yapmak kolay değildir. Yani notlarım elimde olmasa ben de hani bunların hepsini kafamdan yazamam. Yazacağım şeyler olur ama bu olmaz. Hani buradaki her şeyi aklınızda tutamazsınız. Çok fazla indeks vesaire var. Hani başka bir şey olsa yaparım. Ama hani bu o kadar şey değil. Hani böyle işin bir mekanik tarafı da var. Geometrinin. Peki. Evet, bu dönemlik bu kadar olsun.